says a recipe for a cake includes some strong baking soda, which causes the cake to expand, because that's what baking soda does. Now the cake always remains in the shape of a cylinder. So, in other words, it looks kind of like a cake. So we have some sort of cake-like shape. So we'll draw a picture. And what do we know about this? The height is 1/2 the length of the radius, which means that our picture is already bad, but that's okay. It's all right. We have the height, and we have the radius, and so the height should be actually much shorter. It's a very short cake here. Now, as it expands, you are continually coating the surface with a special glaze. And so you're able to keep track at the rate the surface area is changing. Now, the problem here, determine how fast the volume of the cake is changing, and include your units, when the cake is 4 inches high and the surface area of the cake is expanding at a rate of 5/2 inches squared per minute. Now the bottom of the cake is not being glazed. That's hard to do when the cake is expanding. And so the surface area is pi r squared, that's the top of the cake, and 2 pi rh is the sides of the cake. All right. So we have some basic formulas already given to us. So there's a couple things to note. So what do we have? Well, let's highlight some things which are important for us to take note of. So we're told that the height is 1/2 the radius. So we can replace the height here by 1/2 the radius. So that's good to know. We're also told some equations, so let's look at those. Surface area and volume. And since we know the height in terms of the radius, we can write everything in terms of the radius. So surface area, that's pi r squared plus 2 pi rh, becomes pi r squared plus 2 pi r times 1/2 r. Well, 2 times 1/2 is 1. So we end up with a pi r squared plus another pi r squared, 2 pi r squared. Okay, that's the surface area for a given value for r. For volume, well, volume, pi r squared h, but again, we replace pi r squared 1/2 r, or 1/2 pi r cubed. So there we go. So there's some other things that we're told. We have some things about the cake is 4 inches high. Oh, probably should have done everything in terms of h. That's okay. So if the cake is 4 inches high, that says height is 4 or r is 8. All right. And we have a rate. So whenever we see a rate, well, that means a derivative. So what derivative is this? Well, it's the surface area. So we're going to say the change in surface area with respect to time is expanding, which means it's getting bigger, so positive 5/2. So we're translating the information from text format into something more mathematical, because we feel more comfortable doing manipulations of mathematical expressions. So we're getting to our comfort zone. All right, so that's the problem, the pieces, but now let's say, what's our goal? Well, it says, how fast is the volume of the cake changing? So our goal is to find what? What are we after? Yeah, dv dt. So here's the interesting thing. We think about what rate do we know? We know surface area. And we want to have volume. Here's the challenge. Do we have a formula that relates surface area and volume? Not yet. Now there's 2 roads to take. And I will say that, well, there's actually 3 roads to take, which is to get the wrong answer. That was the road most traveled. But in terms of getting the right answer, there's two different roads you can take. So let's talk about what the 2 roads are. So the first road, which is not the preferred road, but we might as well point it out. So we'll go through, is to say, get a formula that involves both surface area and V for volume. So in other words, we want to get a single formula that relates surface area and volume together. And if we look at these things, we can say, well, notice here what we can do is we can say that for instance, r squared is surface area over 2 pi, and r cubed is equal to twice the volume over pi. So we say, okay, what can we do? Well, if we take the expression for surface area and we cube both sides, we get surface area over 2 pi quantity cubed, and that's equal r to the 6. And if we square the formula for volume both sides, we get r to the 6 equals 2v over pi squared. So the punchline here is we now have an expression that we can actually work with. It says surface area cubed over 8 pi cubed is equal to 4 volume squared over pi squared. And if you rearrange things, you can say something, for example, volume squared is equal to, well, multiplied by pi squared divided by 4, surface area cubed over 32 pi. And now you have a single formula, and then you take the derivative of both sides with respect to t. So that's one way to do it. But I don't want to go that route, because I want to talk about there's sort of an interesting second route, which is to say, okay, the other way is to say, what do we have? We have a formula that relates volume to r, and a formula that relates surface area to r. So what we'll do is we're going to introduce an intermediate step, which is, let's look at dr dt. So I can relate, how does the surface area change with the radius? And then I can ask, how does the volume change with the radius? And I can combine those two things together. So let's start by looking at our expression for surface area. If we take the derivative of both sides, we'll get that the derivative of surface area with respect to time is equal to, what's the derivative of the right-hand side? 4 pi r and dr dt. Now what we do is we plug in what we know. We know r is 8. So this 4 pi r becomes 32 pi. And we know dsa dt, because it's right here. That is 5 over 2. So we can take this information and solve. So we can get that dr dt is equal to 5 over 2 divided by 32 pi, which makes it 5 over 64 pi. Okay, so there's our dr dt. Now that we know dr dt, come into our next relationship for volume. Take the derivative of both sides. Derivative of volume with respect to time. Well, that's the derivative of volume with respect to time. Equals, what's the derivative of 1/2 pi r cubed with respect to time? 3/2 pi r squared and dr dt. Now, we are looking for dv dt. That's good. So we don't have to do anything fancy there. We have 3/2. We have pi. We know what r is. R is 8. 64. Then dr dt is 5 over 64 pi. So the pi's cancel. The 64's cancel. And we're left with 3/2 times 5, 15/2. So that's dv dt. We're not quite done. What are we missing? Yeah, because there's somewhere in here where it says with units, which means we have to figure out what the units are. Well, the way to figure out units is you look at this expression dv dt. So the units are, what are the units of volume? Well, what are we measuring our sizes in? We're measuring our sizes in inches. So our units for volume will be inches cubed. How about our units for time? Minutes. And we see that over here, because our dsa dt is inches squared per minute. So 15/2 inches cubed per minute. And I think that's the more elegant solution, because we don't have to actually solve for volume or solve for surface area if we do this. Whereas in the other one, we would have to actually solve for volume and solve for surface area. So there's this idea, it's like, look, sometimes you can chain things together. So if you have several relationships, you can work through and build up from one to the other. All right, that was a fun problem. So what's today? So today's topic is going to feel really familiar. Now, we've done almost all this before, but we're just giving it another name. So we've talked about differentiability, and we've said, okay, what does it mean to be differentiable? Now, there's sort of a formal thing that says we're differentiable if we can take a derivative. But the sort of logical thing we think of, or rather our intuitive way of thinking about things, is we say something is differentiable if locally we look flat. So when you zoom in really close, zoom in on that curve, it looks like a very flat line. So that's what we mean by differentiable. So we're going to talk about today is linearization. So linear is basically, you should think of that as being flat. So it's hard to say isation part, but the isation part says make it flat, or use the flat thing to work with it. So the question is, okay, what's our flat thing? And the answer is, our flat thing is the tangent line. So that's the punchline for today. We're going to say, look, I want to approximate my function, this, say y equals f of x, and I want to say, what does it look like nearby? It looks like something flat. What do I call that flat thing? And how do I use it? So there's a couple of important things to point out. Namely, when is the linearization good? And the answer is, it's good if you're near. So that is to say, if you look close by, you can see that there's very little difference. So if you cover up the parts far away, it's hard to distinguish the line from the function. But as you move farther away, you can see that the function and the line start to get very different from each other. So one of the things we note is that linearization is only good when you're near. The further out you move, the worse it gets. And that's okay. That's sort of logical, because we had to zoom in. So we're saying the zoom, you have to be nearby. All right, so the linearization is our tangent line. So sometimes you'll see this L of x. It's f of a plus f prime of a times x minus a. And again, we're best when we're near a. Now, there's another way to get linearization, which is if you go back and think about the definition of the derivative. So we said that the derivative f prime at a is the limit as x approaches a of f of x minus f of a over x minus a. Okay, so what do we do? Well, we know how limits work. Limits say what should happen. In particular, as x is close to a, what should be true? Well, as x gets close to a, this expression here, f of x minus f of a over x minus a, should be getting close to whatever the value is that is at the end, what we call f prime of a. So f of x minus f of a over x minus a is approximately f prime of a. Now you do a little bit of fancy math called multiply. So you get f of x minus f of a is approximately f prime of a times x minus a. And the other thing that's a little fancy is you add. So you add the f of a across, and you see that f of x, lo and behold, is approximately f of a plus f prime of a times x minus a. All right, so that's good. That's another nice intuitive way to see that. So what's the goal? Why do we care about linearization? What are we going to do with it? And the answer is, we can use the linearization to get an estimate for what the function is doing. Because the linearization is approximating the function. So maybe I have a function that's really hard for me to actually compute a value explicitly. But I say, look, I know how to compute something really close, and I can use linearization to get an estimate. So one of the big things that we do with linearization is say, let's get an estimate for what something should be. And really, it's one of the powerful things about calculus is estimation. How do we get an estimate for what we want? So let's look at a problem. So find the linearization of f of x equals square root of x at x equals 64. So that's the first part. And then we'll wait for the second part once we've done that. So f of x equals square root of x. Now, since we're doing calculus, we're not going to write f of x equals square root of x. What are we going to write? X to the 1/2. Because calculus works really convenient when we have things in our exponents, those numbers. All right, so linearization, just again another fancy way to say tangent line. So we're going to need to get the derivative, because that's going to give us our slope of our tangent line. All right, derivative of x to the 1/2. 1/2 x to the negative 1/2. Now in this case, since we're going to use it, I'll go back to using square root symbol, 1 over 2 times square root of x. Now we're going to find it at a particular place. So linearization happens at a point. So we plug in 64. The square root of 64 is 8. All right, how about the derivative at 64? Well, that's 1 over 2 times the square root of 8, which is 1 over 16. So we can say then that our linearization is that L of x is, and I'll write down the long way first, f of a plus f prime of a times x minus a. So that is going to be f of 64, 8, plus 1 over 16 times then x minus 64. Okay, so that's the first part of the problem. Find the linearization. Now we come to the second part of the problem. So what does the second part say? Use linearization to approximate the square root of 65. So now we want to do the square root of 65. Notice that the square root of 64, that's pretty straightforward. Most of us know the square root of 64 by heart is 8. Not many of us know the square root of 65 by heart. So how do we use this? Well, what's the idea? The square root of 65. How does this relate to what we've done? Well, notice that we have the square root function. So I can think of the square root of 65 as what happens if I plugged 65 into my function. Because that's what it is. The square root of any number is that f of that number, because the f function is the square root function. So now comes in linearization. Linearization says, hey, I'm a pretty decent approximation if I'm not too far off. And 65 is reasonably close to 64 to give us some insight. So I can say that the function at 65 is approximately what the linearization is at 65. Okay? So the picture here is something kind of akin to what you see here. So you have, here's our point. So this is at A. So think about, here's A. And what I'm saying is, at A, we're exactly right. But if I'm near A, I'm not too far off. So that's what we're doing, is we're saying, okay, I'm going to get a little over, and I'm going to use that as my guess. So we plug 65 in, and what do we get? Well, that's 8 plus 1 over 16 times 65 minus 64. And so that's 8 plus 1 over 16. Now, since we're doing an estimate, let's see, 1 over 16. I believe, let me think about this for a second. I believe this is 0.0625. Is that? Yeah? Okay. Now, are we close? What do you think? Are we close? Now, unfortunately, I don't have a calculator, but I suspect many of you might have some piece of technology that we can check this with. I'm pretty confident about the 8. So I'm going to go out. I'm 99% certain about the 8. In fact, I'm also pretty confident about the 0. And because I believe calculus is good, I'm going to go ahead and say the 6 should be true as well. Does anybody know what the next few digits are? 2, 2, and then maybe one more? 6. Now, that says, look, the estimate, which we did not work very hard for, is pretty decent. It's up to the first 3 digits. If you were an engineer, you'd almost say that's perfect. So they might say, okay, how do I get that next digit? Well, we save that for Calc 2. Good stuff is coming. Good stuff is coming. All right. Well, let's do another one. Use linearization to estimate the cubed root of 137. Now, in the previous example, we actually had a function given to us. Here we don't have a function given to us. So we've got to think about what's the right function. So the cubed root of 137, what's the right function to think about in terms of the linearization? What are we trying to linearize? The cubed root is a pretty good candidate. Because you can think about it as like, what's happening is you're plugging 137 into the cubed root expression. So we're going to say, okay, so our idea is we're going to linearize the cubed root of x. Now, that's not quite enough to finish off the problem about what we need to do, because not only do we need to know what to linearize, we need to know where to linearize. So now we've got to start thinking, is there some number reasonably close to 137 which has a nice cubed root? So start thinking about your cube. So like 1 cubed is 1, that's not really good. 2 cubed is 8. 3 cubed is 27, we're getting closer. 4 cubed, 64. 5 cubed, 125. That's pretty good. And 6 cubed is bigger than that. Yeah, so we're not going to go with 6. Okay, so the idea is we're going to linearize here at the point 125. And we're picking 125 because 125 is the value that's nearby the 137, and we know how to plug it into our function. So we're picking something that has both properties. We want to be near the point we want, and we want to be able to evaluate it. So cubed root of x, of course, in calculus, what does that become? X to 1/3. So this will be very similar to the previous problem. What's the derivative? F prime of x? Yeah, 1/3 x to the negative 2/3. All right. Or if you like, that's 1/3 times the cubed root of x squared. All right. Now we need to plug in 125. So we already did the function of 125. We said that's 5 because we were looking for a good cube root. So that's not so hard. How about f prime of 125? Well, that's 1/3 times the cubed root of 125 squared. And so all we have to do is square 125 and take the cubed root. That shouldn't be too bad. Or maybe we can do it in a better way. Because we made a choice here, we could have made a better choice. Instead of first squaring and then taking the cubed root, we could have taken the cubed root and then squared it. Let's do that, because that's probably going to be something we can actually do without a calculator. So 125, cubed root it, and then square it. Cubed root of 125, 5. Squared is 25 times 3, 75. That's something we can do. So our linearization will be the function at 125 minus f prime at 125 times x minus 125. Oops, sorry, this is plus f prime. Sorry. All right. So we plug in what we know. We have 5 plus 1/75 times x minus 125. So now we're ready. The cubed root of 137, which is what we're trying to approximate, is equal to what happens if we plug it into our function. And now we use the fact that our function is approximately the linearization. So that's approximately the linearization at 137. All right, well, now we plug in. So we're going to get 5 plus 1/75 times 137 minus 125. Well, 137 minus 125, we can do that. What is that? 12. Do 12 and 75 have any common factors? They have a factor of 3. So I can write this as 5. If I factor the 3 out of the 12 and the 75, I'll be left with 4 over 25, which happens to be the same as 5 plus 16 over 100. And you're probably thinking that's the wrong way to simplify. You don't usually multiply by something, you divide out by something. But 16 over 100 is easy to convert to decimal. 5.16. Now, that's our guess. So we now have a guess. The cubed root of 137 we think should be about 5.16. Well, let's find out. We might want to know. Well, I'm pretty confident about the 5, and I'm even confident about the 1, and I'm going to bet you the next digit is a 5. We'll talk about why I made that bet in a second. That's my bet. Okay, what is it really? 5.155, and I think there's a 1. ... And again, you'll notice, pretty reasonably close. In fact, if you took 5.1551 and you rounded it to 2 digits, you'd end up with 5.16. So that's pretty good. Now, how did I know that this was going to happen? That I was going to be wrong in that direction? So here is when we use our little bit of knowledge. Cubed root of x, if you look at cubed root of x for positive numbers, it looks a lot like square root of x. It's going up. So that's what the cubed root of x looks like. And so what happens is we're using a tangent line. So our tangent line is going to be here. How does the tangent line compare to the function? The tangent line is above the function, which means that anytime I use a tangent line to make a guess, which is what we're doing, I'm going to be a little bit above where I should be. And so that's why I said, okay, 5.16 is going to be above where I should be, so I should go a little bit below, 5.15. So we're going to talk a little bit more about how we can recognize, when is the function sort of going up below the tangent line, when is it going above? That's a topic coming up in the near future. All right, well, the next thing is we can, again, think about linearization in another way. So this is just sort of rearranging. It says, hey, I can rewrite my expression. I move the f of a back and put it with the f of x. So I have f of x minus f of a, which is really saying what's the change in the outputs, or change in y. Remember that we use that symbol delta. The delta represents change in. So the change in y is approximately this f prime of a times x minus a. And x minus a is our delta x, or change in x. So my change in y, the rate at which y is changing, is approximately f prime of a times change in x. Now, this probably won't surprise you if you think about it, because this is saying, if you start it, it says like really f prime of a is about change in y over change in x. And you're like, oh yeah, change in y over change in x, that's just the slope. So it's a derivative. So yeah, it should be very close. So that's good. Now, how do we use this? Well, it says if I want to estimate how does one thing change with another, I can use this value here, or this relationship. It's giving us a way to estimate how much our output will change based on how much our input will change, or vice versa. Maybe we want to say, I only want my output to change by so much. What's true about how much my input can change? And oftentimes, a precise expression is not needed. An approximate expression will work just as well. So we're going to do some examples now in this direction. So suppose I have the following. Y is 5x cubed minus 4 times e to the power 3x minus 6. And I'm told that x is near 2 in the following way. X is within 2 plus or minus 0.05. So the picture here is I have some function doing something. I'm not really sure what it's doing. But I have 2. And what's happening is I'm going to be within some interval. So within 0.05 means I can be down as low as 1.95, and I can be up as high as 2.05. Now what I want to do is I want to use linearization to estimate the corresponding range for y. Now if I were exactly 2, what would happen? Well, if I was exactly 2, I would just plug 2 in. So at 2, what do we get? Well, 5 times 2 cubed minus 4e to the 0. 2 cubed is 8 times 5. 40, subtract 4 times 1 gives 36. So that would be if I was exactly 2. But remember, I'm in this sort of window here. So the question is, what I'm trying to do is get a handle on how much could I vary upstairs. So what's this interval up here? How much am I going to vary from this 36? That's what I want to estimate. I'm not going to get it exact. I'm just after an estimate. So how does it go? Well, we use the formula here. We know that delta y, the change in the y, so this right here, let's first go on here. Here's the delta x, which is 0.05. The delta y, that's this mark up here, how much I can vary. So we have that delta y is approximately f prime of a delta x. And f of x is our function. So we start by taking the derivative. What's the derivative of 5x cubed? 15x squared. And now minus 4 times the derivative of e to the 3x minus 6. What will that be? It'll become 4 times 3, because the derivative of 3 comes down. So I'll write it as minus 12, e to the 3x minus 6. So that's the derivative. I want to evaluate it at 2, because I'm at 2. So f prime at 2, well, I'm going to get 15 times 4 minus 12 times 1. Because 2 squared is 4, e to the 0 is 1. That'll be 60, subtract 12, which makes 48. Now that's not saying I'm going to move by 48. That's saying that's what the rate of change is. For given a little change in the input, that's the corresponding amount we scale by for the change in output. So this 48 is what goes into there. So our change in y, how much y can vary, is approximately 48 times 0.05. which is our change in x. Now, if we take 48 times 0.05, what does that become? Well, if it's throwing you off, don't worry about the 0.05. Just think of it as 5. How about 48 times 5? Can we do that? It's 240. If you think of 40 times 5 is 200, then 8 times 5 is another 40. So it's 240. Now we have to move the digits over 2 places. So we'd have 240, but then we move our decimal over by 2. So we get that our change in y is approximately 2.4. So the corresponding range for y, and again, it's an estimate, it's not saying exactly, it's an estimate, would be the 36, which is if we were exactly at 2, but then plus or minus up to 2.4. And that's the answer. Okay. Well, now let's do some word problems. Good word problems. So you've recently been hired as the chief architect for one of the pyramids being constructed by Pharaoh Sneferu in Egypt. After some consultation, the Pharaoh has agreed to a pyramid design that is 500 cubits wide and 300 cubits high. A cubit, by the way, in case you don't know, that's a system of measurement in ancient Egypt. So the volume of a pyramid, so we should probably draw this. So here's our pyramid. All right. There's the back side that we can't see. Okay, so here's our pyramid, and let's see, the 500 cubits wide, so that's down here, 500. and 300 cubits high. Okay, so 300 is the height. All right. Now the volume of a pyramid is 1/3 b squared h. B is the length of one side of the base, and h is the height, so that the pyramid will require 25 million cubic cubits of stone. All right. Now after getting in touch with your stone contractor, which of course if you're going to build a pyramid you should have a stone contractor, you discover that there are only 23 million cubic cubits of stone available. The pharaoh gives the go-ahead to build the slightly smaller pyramid, but the same proportions. So we can't build this pyramid, but we're going to build one a little bit smaller that looks like just sort of a shrunk version of this one. So it's just a little bit smaller, same ratio of base to height. Use linearization to estimate how many cubits smaller the base of the pyramid will end up being. So our goal here is we're trying to figure out what is our change in our base. Now what do we have? Well, we went from 25 million cubic cubits to 23 million cubic cubits. What is that telling us? Well, it means we lost 2 million cubic cubits. So given the change in volume is negative 2 million. So that's the problem. We want to find out what is the change in base approximately, and again it's an estimate, and you might say, how do we know it's an estimate? Our key is that they used the word estimate. That sort of gave it away that it's an estimate. So we want to estimate what is this change in the B, the base, given that we know the change in the volume. Well, so we start. Say, okay, what do we know? Well, we start with the volume of the pyramid. So the volume is 1/3 times b squared times h. Now, the problem is, what do we do with the h? How do we handle that? Notice there's a key word here, or a key phrase, same proportions. So that means that when we shrink b, we should also shrink h. So what we should do is we should look at the proportion of b to h. So if we think of our pyramid, here's our generic pyramid. It's b cubits on the side, h cubits high. These two are proportional, which means I just scaled the big one down to get the smaller one. Well, when you scale, everything scales. So the ratio scale. So 500 versus 300, so if I look at that ratio, length of the base to the length of the height, is the same as b is to h. So that's what's happening. So the good news is lots of zeros cancel, and we can conclude, if we rearrange this, so move the h, move the 300 over 500 across, that the height is 3/5 times the base. So we can update our expression for volume. Volume is 1/3 times b squared times 3/5 times b. We can get the 3's to cancel, and we end up with 1/5 b cubed. So now I have an expression for volume in terms of base. So now I'm trying to estimate the change in volume over change in base. So I can think of this is sort of my function of my base, f as a function of b. So we would get that the change in volume is approximately the derivative evaluated at the right point times the change in the base. So let's go through and work this out. So what is our f prime of b? Yeah, 3/5 b squared. Now, the question, which b do we use? Well, which b do we know? We only know one value for b, so that helps narrow it down. We only know the b equals 500. We don't know the smaller b, we don't know that. We're trying to get an estimate for what it is. So we're going to use the linearization at 500 to figure out what's going on. So here we go. So we get the following. Delta V, well, let's write down the whole thing. Delta V is approximately 3/5 b squared delta B. So negative 2 million is approximately 3/5 times b squared, which is a 500, times another 500, times delta B. Okay, well, let's hope things work out. Well, good news is 5 goes into 500. That's a 100. 100 times 500, well, let's divide both sides by a lot of zeros. So there's 1, 2, 3, 4. We're going to knock off 1, 2, 3, 4. So we divided both sides by 10,000. You just knock off zeros. 2, 2, 2, 2, 2. So if we have that, what do we have? We now have negative 200. On this side, what's left is 3 times 5 is approximately 15 times the change in your base. So the change is approximately negative 200 over 15. Well, but both these terms are divisible by 5. So we get negative 40 over 3. Now, 40 over 3, negative what? Qubits. Qubits. All right. And there's our answer. Now, in case you're wondering, is Sneferu a real person? Yes, Sneferu was a real person, and he built a pyramid, as many pharaohs do. Do you know what pyramid he built? He built the pyramid that looks like this. It's called the bent pyramid. And if you look at it, it's like, oops, they ran out of stone sort of like halfway through. It's like, okay, we better make it go really fast at the top. So he did not work well with his stone contractor. Let that be a lesson to us all. Always check with your stone contractor before you build a pyramid. All right. You've recently started a new job. Well, this is fantastic. It's wonderful how you always have these new jobs. You just got hired, you have a new job. All right, you're the quality control officer in the new widget factory. The company slogan, you fidget, we widget. Now, a new machine has been installed that takes a rod of length X inches. So here we go, here's our rod. And there's X inches here. And it returns a widget, so it's a machine. So we have this machine here. All right, we don't know what it does, but out of the machine comes our fancy widget, whatever that is. Okay, so the rod goes in, the widget comes out. All right, what's the size of the widget? Well, it's x squared plus 3x plus 2. So this comes out, it's x squared plus 3x plus 2. Now, ideally, you want all your widgets to have an output of size 20, which would correspond to starting with a rod of exactly 3. Well, that's good to know. So if we put in a 3-inch rod, out comes a widget of size 20. Perfect. Perfect. Now, there's a problem. Not all rods are exactly 3 inches. In fact, probably no rod in the world is exactly 3 inches long. There's always going to be an error. So, what's going to happen? Given that you want the widgets to be within, say, a half of 20. So the sizes of the widgets can be 20 plus or minus a half. How much error can you give for the length of the rods? How much are we willing to tolerate? So this is actually an important type of evaluation, because you know you're going to have to always work with things which are not perfectly measured, and you have to say, look, how much am I willing to budge? So what do? Well, here's our f of x. And what do we know? Well, we know that f of 3 equals 20. And we also know that we want to be within plus or minus a half. So plus or minus a half. This right here is our change in y. So our change in y, our change in y is a half. That's how much we're willing to tolerate. So we say our formula says that the change in y is approximately. Now, how do we know we want to estimate? Because it says estimate. Yeah. So whenever you see estimate, pretty much, if you see the word estimate, anytime this semester, it's like use a tangent line in some way, shape, or form. So the change in y is approximately f prime at 3 times the change in x. We know the change in y, that's a half. What is f prime of 3? Well, what is f prime of x? F prime of x? 2x plus 3. So f prime of 3? I think that's 9, right? 2 times 3 is 6, plus 3 more makes 9. So 1/2 is approximately 9 times the change in x, and therefore the change in x is approximately 1/18. 1/18 what? Well, the units of x, 1/18 inches. So that says, look, if I want the output to be within a half of the right size, and we aren't saying what the units are for the size. Maybe a widget is a 3-dimensional thing. Maybe it's a 1-dimensional thing, which would be really interesting. But who knows? But at any rate, we're not saying how big, what the sizes are for the widgets. We're just saying, all right, what's the tolerance? And the answer is, look, the rod has to be within 1/18. All right, let's see. Estimate how much error. That's the answer, 1/18. So, okay, good. Now, one last thing for today. There's something called differential notation. Now, here's how I like to think about it. So differential notation, you have these two ideas. You have what is the function doing versus what is the linearization doing. So when you see that delta, the delta corresponds to what's the function doing, what's the change in the function. So the dy says what's the change in the linearization. So in the picture below, I have my function here, and I have my linearization. You can tell which one is the linearization because it should be a line. It's in the word. Linearization starts with the word line. So the delta x is the same as the dx. If I want to know what's delta y, well, what I do is I say, how much does my function change? So I start at this value, and I'm going up to there. So that is the change in the function, the change in the y values for the function. On the other hand, if I want to say how much does the line change, I start at the same start place, but I only go up to where the line goes. So that's the d sub y. And linearization basically says dy is very close to delta y. Now, as we go on, you will see this showing up a little bit towards the end of the semester, where you'll see things like dy is f prime of x dx. And it's very tempting to say, well, that's totally obvious because we said that dy over dx is f prime of x. But dy and dx here are different, they're one thing. It's dy over dx is one thing, not two separate things. And it's a very confusing concept. So the good news for you is we're not going to test you on differential notation. But if anybody ever says, what is differential notation? The idea is, oh, you're like operating on like the linearization. It's basically mimicking the function. All right, that's it for today. And we'll see you next time.